afternoon, everybody. You all know me. My name is Ali Kujuri, and on behalf of the Engineering Science Department and the School of Science and Technology, I would like to welcome you all to this fourth lecture in the series this year. And it's the 127th lecture in this series since 2006. Before I start introducing our guest speaker for today, let me mention that first we got to thank Mr. Sharam Mariwani, who is really helping us in doing a lot of things related to this lecture series, and then also Ronnie Goodland, who has ordered the pizza and is going to arrive at 5:30 today. But let me mention that after the talk, we have some, I mean, this place is going to be used as an open house for the Tech High down the stairs, so we're going to be here. So can I ask you to have your pizza quickly, and so that we can clean the room and then make it ready for them. Now, the next lecture is titled Gold Foams as Advanced Biomedical Device Coatings by Dr. Erkin Seker, Associate Professor in Electrical Engineering Department, UC Davis. It's going to be on the 2nd of November at the same time, the same place. Our guest speaker for today is Mr. Rowlands, and the title of his talk is Internet of Things Testing Challenges. Mr. Rob Goodlands received a Bachelor of Engineering degree in Electrical Engineering from University of Canterbury in Christchurch, New Zealand in 1971. He was a transmission engineer in the New Zealand Post Office for 22 years, followed by 21 years with Hewlett-Packard and Agilent in the San Francisco Bay Area in business development and sales of communication test equipment. He is semi-retired, but still selling test equipment for Gap Wireless. Rob is a life member of the IEEE. So let's just give him a hand.
So if you know anything about the IEEE, if you add up all those years and those two jobs, that's all you need to be a life member. So it's not a huge, huge deal. But it's a nice little accolade. You get a certificate. Shows you paid for I think 35 years, and then you're free after that, aren't you, Doc?
Right.
Where is here?
Yeah, that's on my just have to do a little. But first, while we get started, Internet of Things. What's a thing? Give me some examples of some things.
Coffee maker.
And what in particular do you need to know about your refrigerator, apart from how much beer it's got? Another thing?
Lights.
A watch? What kind of watch? And why is it smart? Good. Another thing?
Lights.
Expand.
Light. Lights.
Okay. And what do you do those for?
Would you talk louder so that you can be heard?
You can like connect it to Alexa, and like give it commands to turn on and off the lights.
Okay. Now there's a little secret about that, because if you're trying to set up for a romantic dinner and you're trying to dim your lights, if you dim an incandescent light, they go nice and warm and red. If you try and dim an LED, it's still bright. so if you're planning a romantic evening and you've got LED lights, find an alternative to dimming the lights. Another internet thing.
Speaker.
What?
Speaker.
Look, what kind of speaker?
The Google speaker. You can control all your stuff.
Okay. Do you have a commercial example you'd like to give?
You can select reminders, reminders, alarms, control lights,
Okay.
and stuff.
Are you able to pick up my audio?
Yeah.
Okay. Another thing?
Just various sensors.
Okay. For what kind of things?
Just for like anything. You want to like measure stuff.
This is a little sensor that's been in my wife's beehives for the last 6 months. Okay? And this little guy here, it's not dirty, it's got focus on, which is like these two in the kind of gaps. So this is a temperature and humidity sensor. It's been sitting in my wife's beehive, I think from the middle of May to the end of August. And when I connect that to my iPad through Bluetooth, ta-da,
This size is not there. Okay, okay.
no internet connection. So need an internet connection. So this little guy here costs $50. Hi, how are you? Costs $50, and let's have a look at the year. Let's have a look at the month. At the moment, we can see the temperature. It's been going up and down every day. Let's look at the day. Less the week. So there's the temperature going up and down. The humidity was 35.4%, and it's been dropping. I live in Marin County, and as you can see, the temperature goes up and down from day to night, as you might expect. This little baby sits in the beehive and communicates through Bluetooth to any device, be it an iPhone or a iPad or anything like that. Got a built-in battery. Battery runs for I think about 1.5 years, and it acquires the data without any connection to anything. So I don't have to go out and do anything. Anybody know what this is? Have you seen anything like this? Comes from Amazon. Push button. Very good. Very good. Amazon has what's the trade name for it? Yeah, it's a catchy name. We can't remember. Anyway, what it is, Amazon sells these things for $5, and you can buy one for Tide, you can buy one for diapers, you can buy one for dog food, and then every time you want more diapers or dog food, you press the button, it links through your Wi-Fi network, and Amazon is glad to send you another part of dog food. What this one is, this is a generic IoT button. And this generic IoT button can be configured to do anything you want. And it's actually configured so that when it's at my house and my wife presses a button on there, it sends me a text message saying, call home, you idiot. Okay? You haven't called for a while. So it's a IoT device, but think about what's in this IoT device. What's the most important thing in that IoT device?
Communication.
Oh, well, yeah, before the communication.
The wireless?
No. The button. Okay, so the button is a sensor. The button is a sensor of your need for new dog food or my wife's need to communicate with me. It communicates through, I think I told you already, but do you remember? No. Wi-Fi. Communicates through Wi-Fi to what? Yes. Where's go through my Wi-Fi? Where's go after that?
Router?
Well, through the router. But after the router, where's the beautiful setup? The server, and do you know who runs the server by any chance? It's not difficult, yes. Amazon, yes. So Amazon runs a network of servers for the Internet of Things. And Amazon Web Services, AWS, is one of the 3 big vendors of cloud servers for IoT. The other ones are IBM Bluemix and Microsoft Azure. And I'll just move on to my presentation now, but before we do that, for some reason I'm not seeing, it's supposed to have, what I wanted to show you, that when this baby was in the beehive, the temperature was almost solid at 96 degrees for 3 months. Isn't that astonishing? So right through May into the end of August, the temperature in the beehive didn't vary by more than about half a degree. Bees are wonderful, aren't they, what they can do? Okay, let's move on to my presentation. And my presentation is very much My presentation is very much based on material I've stolen from Keysight. And I used to work for HP, Agilent, Keysight, whatever you want to call it today. And so I've worked with some of the people in Fountain Grove and elsewhere on developing these slides. So it's not all original material, that's for sure. I'm going to talk about what we need to test, and I'm going to talk about what we can test, and should we even test, do we need to test. But I'm thinking, looking at the audience here, a little bit of a review of IoT is not a bad idea, is that right? Will I be insulting you guys if I review some of the IoT developments? Probably you don't. But, and sorry. So if you forgive me, stop me if you want me to hurry up. So the point about IoT today is we've got lots of different connectivity standards. So what have I spoken about today in terms of connectivity of our things? Wi-Fi, Bluetooth, but there's also other connectivity standards. There's Zigbee. You know what Zigbee is? Used for controlling lights. You were talking about lights. LoRa. LoRa is a Wi-Fi technique that's been expanded out beyond the typical reach of Wi-Fi. What's the typical reach of Wi-Fi? How far can you go with Wi-Fi? You're not eligible to answer. You know, the non-faculty, how far does Wi-Fi go? 150 feet, that's not a bad choice. Probably less, actually, unless you've got a really, really powerful router that you might not have all that. It depends. But typically Wi-Fi, anything between 50 feet and 150 feet. Except, some people have actually made Wi-Fi work for 150 kilometers. Okay? They've done that by using gain antennas and by modifying the firmware on the routers. But that's Wi-Fi. There's also another standard which is quite widely used called Sigfox. Sigfox is like our cellular service, but it's not cellular. It's a similar standard. You buy service from a company called Sigfox, and the sewers of San Francisco are being monitored using Sigfox. So every flow sensor in the sewage system inside San Francisco is connected through the Sigfox network. Why do you think they went through a private Sigfox network rather than going through AT&T or Verizon or T-Mobile? Any ideas? Why would you want a private network?
Confidentiality.
Confidentiality is one thing, sure. Another reason? Who knows what happened in Houston, in Florida, and Puerto Rico? So what was so of those three disasters, exclude Santa Rosa, of those three disasters, which one had good cell phone service, do you know? It's quite interesting, this. Puerto Rico had the worst, let's say that. Start from the bottom. Florida and Houston had similar problems with inundation of water and so on. Very little building damage in Florida. Virtually all the cellular service was wiped out. Houston was the other way around. 95% of the cellular service in Houston kept running. In San Francisco, if they were running on cellular, there was a big flood, cloudburst, tsunami. You think the San Francisco sewage network wants to run on AT&T knowing you might fall over. So that's why they run private. Security is another issue too. It's not. I don't think it's the main reason. So what? Here we go. Sure, I'm going to go backwards. I knew this was going to be a problem. Forgive me if I screw up. Okay. Yeah, this is easy. So what Keysight is doing for IoT is monitoring these standards, reducing the cost of failure, and the classic one that you guys didn't mention was your power meter. Maybe you don't pay power bills, I don't know. But your power meter is a thing. It's connected by 900 meg radio into the PG&E network. Did you know that? No longer does a man come around and stumble through your garbage cans to read the meter. We're trying to lower the cost of test because a typical thing is a very, very low cost. This spectrum analyzer that we're going to use later on costs about $30,000 and typically is being used for testing equipment worth anything between maybe $5,000 and $150,000. you're testing a thing which costs next to nothing. This costs $25. If you're testing that, can you afford to have expensive test equipment? So scaling the test equipment for mass deployment of devices is key to where Keysight's going on its IoT direction. And what's interesting about this and our cell phones? What's going on in the power business here? What are our cell phones running on? How long does this iPhone 7 battery last? Normal use. A day? How long do you think this lasts, this IoT thing?
5 years.
5 years? How long do you think this guy lasts? So typically IoT devices are supposed to operate in the 1 to 10 year range. You don't want to keep going up and change batteries. Changing batteries on these is not so hard. A lot of IoT devices don't have removable batteries. Oh, this doesn't have a removable battery either. Imagine that. How do they do that? So optimizing battery life is a key issue with IoT because, oh my gosh, sorry. Optimizing battery life is really important because something that's really interesting about IoT devices, I'm going to pass one around for you. I apologize for the fragility of this, but this is a little IoT LTE node. I'm being quite careful about what I say here. It's an LTE node. It's connected to a battery pack, and as I pass it around, just have a look at how much current it's drawing, because that little device with the meter is showing you how much current it's drawing. But is that really the amount of current that's being drawn, or is it just the average? And you know, a typical IoT device has to last 10 years. So the last thing you want to do is to use up all the battery, just doing dumb stuff. You only want to use battery when the stuff is doing. And what Keysight has done is come up with a set of battery tools designed for power consumption measurement. So this little thing that I'm passing around here is not that power consumption device. It's way more sophisticated than that. And what it does, it plots against time the power consumption of your IoT thing to determine the area under the curve. You look at current, this is time, and the area under the curve is time times amps or milliamps. The 30 watt your capacity is in milliamp hours. So as things wake up, if you've got a Fitbit, who's got a Fitbit? I don't know. If you've got a Fitbit, the Fitbit's quiet most of the time. You press the button on the Fitbit, it wakes up for how long? You got one? 30 seconds?
I have an Apple Watch.
Oh, well.
I don't know if...
How long does your Apple Watch stay on for when you wake it up?
less than... Oh, just light up. Yeah, probably like 5 seconds.
Right. But this watch here cost me $25 at CVS. It's continuously displaying. If I want my Apple Watch to display continuously, the battery lasts a couple of hours. So obviously anything that's going to operate off batteries has to use its battery very sparingly, and obviously the duty cycle of the battery has to be spread out over that 1 or 5 or 10 year life. And determining that power consumption is one of the key things that Keysight's been working on. Radio frequency design. Virtually every internet thing connects through some kind of radio. So we've talked about Bluetooth, we've talked about Wi-Fi. The device I'm passing around here actually connects using LTE cellular. So it's actually connecting to the same service as my iPhone. Okay? Determining whether the device you've made meets the standards that are required in the radio frequency part of the world is another area where Keysight has got major contributions to make. This is looking at stability over time. So run your Apple Watch, put it in a chamber, heat it up, freeze it, shake it, bake it, do all that kind of stuff, and see if it survives. So that's a key thing you need to do. And then there's a zillion standards that you need to meet. So it's all very well to say this phone is an AT&T phone, but does AT&T define the standards by which it connects to the network? It's just designed by the Cellular Telecom Industry Association, CTIA. And if you want to take it to Europe or South America, obviously you've got to meet the standards in different parts of the world. So making sure that these devices that cost, remember, $5, $10, making sure these really cheap devices work worldwide is not simple. So we've talked about where we're finding IoT devices. So the smart home, we talked about lighting, HVAC control. We have a house up at Tahoe, and for 4 years now, I've had a Wi-Fi thermostat on that house. And I can access that Wi-Fi thermostat from anywhere in the world. I've just been in New Zealand for 2 weeks with some people staying in our house. I wanted to see whether they were actually there or not, so I just looked at the remote thermostat. Now, this is not rocket science, it's really simple stuff. But the important thing was I was able to monitor something as indirect as whether the people who were staying at our house were there or not by looking at the temperature to see if they turned on the central heater. So all these kinds of things have been around for quite a while. Health monitors we've talked about. We talked about Fitbits, the smartwatch, the Apple Watch. Hearing aids. Hospitals have more technology in them today than you would ever believe. I don't know if you've been into an intensive care unit lately. I hope you haven't. If you have, you'll see more hardware than you'll see in the electronics side. Smart city. We talked about waste management. We talked about the San Francisco sewer system. If you go around the back of your favorite watering hole, you'll find a very large dumpster. And that dumpster is full of all kinds of stuff. And SSU has a party at the place down here. What's the name of the bar? Thank you. I didn't even know. So we have a party down there, and the next day, the person who comes to the next shift finds the dumpster's full. Now, the problem is the dumpster is not supposed to be emptied until Tuesday night, and this is Thursday. This device, made by a company in Finland, called Innovo, goes in the dumpster. It has a proximity sensor here, and it can measure how much garbage is in the dumpster. And it's connected through a cellular network, and it goes through the cellular network into a cloud to inform the garbage pickup company that they've got work to do. Anyone see a problem with this? This is actually correct. Anyone see a problem with the garbage company being told that it has to pick up garbage? I'm sorry?
Increase cost.
Indirectly, but
If you're not told, then you're not going to.
well, as I recall, most bars I've been to the dumpster isn't exactly locked up. It's usually wide open at the back. Another more subtle thing, try and think out of the box a little bit. So you're a garbage collection company, you're the Roman Park collection company, whatever it's called. And you're supposed to go every Tuesday night to this bar and empty the dumpster. Now,
Yeah, you have to drive like a big truck out there to serve one of those.
you're not thinking deep enough. Think deep enough. Put yourself in the culture of the guy. Think of the negative side of having this. You're at a disadvantage of having this.
Longer sheets for the person
I can't hear you, sorry.
working. With longer sheets for a person working.
Well, yeah, that's one, but there's also a negative side too.
Well, it throws off the schedule, right? Like,
And if you think about it, if you're running a dumpster company, you want to have regular pickups every Tuesday afternoon, or whatever it is, and you don't want some smart-ass person telling you that you have to come down on Thursday because it's a party. You basically have almost a sort of a working class reaction from the garbage pickup companies who don't want to be told how to do their job. So it's a social problem that's brought on by a technical solution. Interesting, huh? So the people who make this, a friend of mine who used to work at Seaside actually is the US sales manager for this. And she said that the garbage pickup companies more or less showed them the door the moment they walked in. Because the garbage pickup companies don't want to change the way they operate. Because your garbage drivers think you're going to get less work this way. Because not only are they learning about full dumpsters, they're also learning about empty dumpsters. So every technical solution brings with it social problems, commercial problems that you can't necessarily anticipate. And this is a beautiful technical solution. The whole thing with the communications through the cellular network and the cloud is very well done, and it's not selling. So what they're doing now is they're actually, the company who makes that garbage sensor, what would you do if you had a warehouse full of those garbage sensors in Milwaukee? What would you do? Say there's 1 million of those sitting in a warehouse in Milwaukee. What would you do?
Maybe try to sell it to them, say that they can tell which houses they can skip to save time.
Well, that was really the problem on the route, because when they know which houses they can skip, that means it's work for them.
You would sell to like companies, right? Bigger.
What they're doing is they're going to themselves in competition with the existing government. So what started off, and my friend Christy started off as a electrical engineer, doing marketing of these wonderful sensors. Now she's running a garbage company. And they're in competition with the Petaluma Garbage Company and all the others who are choosing, for whatever reason, to not be flexible enough. It's back to the taxi versus Uber argument, isn't it? I mean, it's our society has these fixed ways of doing things for which the model we live with today is so enshrined that the concept of on-demand drivers that we get from Lyft and Uber was so foreign to taxi companies, all they could do was object to it. Okay? That's what's happened in the last 5 years. Same thing with this new government. So people resist change and they don't necessarily want to embrace the latest technology just because it's cool. We all think it's cool, so we think this must be great, everyone must love it. But as engineers, we're constantly being stymied by finding things aren't quite as well received out of the society as we think they should. We're all familiar with the checkout stuff, asset tracking. That's a type of Internet of Things, although the typical asset tracking is passive. It's a little RFID device that's built into the clothing or something that you're about to buy. Connected car is a huge thing. And I think the connected car is probably one of the biggest IoT developments, even though to call it a thing is probably being a little bit broad in the definition of a thing. It's not exactly a $5 thing. And the implications of screwing up on your communications with a connected car are pretty significant. So for instance, if you're driving your Tesla down the expressway and there's a stop sign there that doesn't get communicated to your Tesla, the Tesla goes straight through the stop sign and went on. So there's a lot of issues, and the whole issue with insurance and so on comes into this as well. But let's see if we can get to the next slide. Put it back up the way.
F5.
What?
F5, function F5 on the keyboard.
Oh, on here.
You want me to try? It's F5.
All right, now we're back at the start.
Right.
Oh, was that a bit finished? Okay. So, Internet of Things, and back, who mentioned the refrigerator? I think it was you, sir. Yeah. So, have you got a Samsung refrigerator?
No.
We happen to. They're saying 90% of all Samsung's products will be IoT devices this year. I don't believe it. But I mean, we bought our fridge like 4 years ago. At that stage, Samsung had a fridge that actually had a TV in the front. It was a big deal. The TV in the front of the fridge. But they're saying 100% IoT connected by 2020. So that means we'll know what our beer supply is like in our fridges by 2020. And okay, this is the guy who's currently in jail. So how much do we trust him? But Samsung's a ubiquitous company, and you can't deny the possible prescience of what he's saying. So this is what every. This will kill me, Sharon. So this is what every salesperson wants to see, and if those of you pick up my business card, you'll see that I'm a sales guy. I used to be an engineer, now I'm a sales guy. This is what you want to see, up and to the right. And they're talking about 5 connected devices for every user worldwide. Okay, well I look around here, I've probably got about 15. And those of you who've got your smartwatch, and you know, we've got our cell phones and whatever else you've got, it's not that unrealistic for the first world for us to have 5 devices each. This is the big problem. 500 devices per kilometre. Who's been to a concert lately and trying to send a text or make a phone call? What happens? Or a game? No service. Why is that? Why don't you get service at a football game or a concert? Speak up there. Is it too many people in one place, or is it just 40 dimensions infrastructure to serve those people? It's the latter. Truly, it's the latter. I mean, what you're telling me about what you observe, but in fact, the problem is the infrastructure is not scalable. And this is the whole problem with the Internet of Things. So when I've got my 15 devices here, all trying to use the same cell phone tower, wherever it is here, and you guys are trying to text your family to get dinner organised and stuff like that, we're going to end up with a lot of problems. And I don't know, sure, I'm just not compatible with the system. I finished my talk. Oh, thank you. F5, right? F5. F5. Okay, let's just, sorry about this. So all these numbers here can be either considered as hype or they're considered as opportunities. For those of you who are graduating in a year or 2 years, you could do no worse than end up in a company that's developing an IoT device. It might be medical advice, it might be any of these other things we're talking about. It's the growth area. You all want to do software though, don't you? I don't know. What's wrong with engineers these days? A couple of interesting comments on this. This is my little, wherever it's gone, this guy. Who's got a Alexa? Pretty cool, isn't it? Is it cool or is it dangerous? Yeah, it's pretty dangerous to have that microphone going all the time. How do you know that the FBI isn't listening in? There's our garbage collector looking at the skip. This is an interesting one. I love talking about this. The Internet of Cows. Not the Internet of Things, the Internet of Cows. So I was brought up in a dairy farm, and cows have 2 issues where you have to monitor their health. And you know, they have their regular their menses every month or whenever it is the cows have them, but they also have something called mastitis. Mastitis is a disease of the udder that causes the milk to become uncommercial. But every time the cow has one of these issues, the temperature changes. So what you do is you slap a $5 device on every cow. How many cows in a typical cow dairy herd? Does anybody know? How many cows?
200.
300, yeah. 12,000, some 1,000, yeah. In New Zealand, where I come from, it's 5,000. So if you have every cow with one of these sensors on them, you've got an awful lot of IoT devices in a small area. And the farmer then can monitor all his cows. And as the cows come in, they're barcoded on their ears. You can divert the ones that they can't milk or need to take other action with, divert them off into a different part of the cow herd. Pretty exciting, huh? Another one that doesn't show very well is the Infinitive Trees. That's supposed to be a tree. So I've got maybe $100,000 to invest in a forest in, choose a country. What's a nice remote country? Let's choose Nepal. Okay? The country of Nepal, north of India, south of China. I pay somebody to grow a forest for me. And I can go over there once a year and see if the forest is growing and pat everybody in the back. But is the forest actually being managed properly? Are they actually watering the trees or allow them to grow? How about we put a sensor in the root ball of every tree so we can monitor the moisture level of that tree? Now, have you been to Nepal? Have you people been to Nepal or similar third world countries? Yeah. What's the internet infrastructure like there? Is it? You sure? Because the dirty little secret actually is that most of the third world has better cellular internet infrastructure than we do. What they don't have is very good management systems. Okay? So they have the infrastructure there. It's usually put in by Nokia, it's professionally installed, and they actually often have surprisingly good connections back to the rest of the world. But for me to know whether my 300 trees have been watered or not, how much data do I need? How many bytes a day do I need to know what the moisture content of my tree roots is? One? Okay. So it's very low data rate. Now the key to all this is cutting through the bureaucracy. Why would I want to go to Nepal and say, excuse me, Mr. Nepal operator, I need to get cellular service for 400 trees, please. And you'll see a blade sign close to lunch. So you've got to work through that commercial and bureaucratic barrier in order to do stuff like this. I'm going to show you in a couple of slides' time the carriers that will sell you a SIM card today that works in 190 countries. You don't have to talk to Mr. Nepalese cell phone. It's already provisioned to roam around the world. Amazing, huh? So if you're trying to deploy something, if you go and work for a company that's trying to deploy some kind of agricultural monitoring system in Argentina, you don't have to worry about how you're going to get your data back, because the cellular network is so ubiquitous now. Everyone in Nepal's got a cell phone, everyone in Argentina's got a cell phone, everyone in Zambia's got a cell phone. So the infrastructure's there driven by people's need to communicate. And cell phone infrastructure by its ubiquity provides that capability. There's three main layers in an IoT system. You've got the sensors and actuators, which would be temperature, humidity, and all that. You've got actuators like door locks, all that kind of stuff. Then you've got the connectivity, which could be Bluetooth or Sigfox or narrowband IoT. And then up in the top, you've got the cloud. And the cloud is either Amazon Web Services or IBM Azure, Microsoft Azure, sorry, or IBM Bluemix and various others. So you do something with the sensor, the connectivity takes you to the cloud, and then the cloud presents that data back to you or gives you the visualization of that data. The test opportunities here for us as test equipment manufacturers, we've talked about the power drain. Decoding SPI. Who knows what SPI is? SPI is a serial interface that's used commonly to connect sensors to devices. So like this, where's that Raspberry Pi go? Somewhere around here there's a Raspberry Pi that's got a sensor hat built into it. So this is a Raspberry Pi in a little case with a sensor hat on it. There's a whole bunch of sensors in there, and all those sensors communicate with the Raspberry Pi using I2C or SPI. As you go up through the stack, there's a protocol called MQTT. And MQTT is, I don't know if you know what it stands for, is a language for sensor to cloud communication. As you go into connectivity, then we care about RF metrics. How much power is being transmitted by this device, this Bluetooth device sitting in the beehive? Is there enough power to get you from the beehive to where the bees are not, so they get stuck? That kind of thing. Then we're interested in data metrics. BER, bit error ratio, is the fundamental metric of digital communication. And EVM is, if you like, halfway between analog and digital. It's the error vector magnitude. If you know about data conservation, do you know about data conservation? Is there a pen that works? Probably not. Is there a pen behind you, Annie? Yeah. Oh, you got it. Oh, good. Those of you who have done any work in digital will know that amplitude versus phase. If this is a 4-position constellation, this means 1, 0. This means 0, 1. This means 0, 0. This means 1, 1. Say. And as your thanks. All right. So as your signal comes in, it's all fuzzy around here. And if it's a really dirty signal, it gets really fuzzy, and you can't distinguish between all the different constellation points. And the radius of the worst constellation point is called EVM, error vector magnitude. And error vector magnitude is a fundamental metric of the conversion from analog, which our whole world is analog, it's not digital, I'm afraid. When we go from analog to digital, we're trying to discriminate between various analog signals to make a digital 1 or 0 determination. Then there's compliance. One of the big problems that's going on now, we've talked about the rock concert football game problem, but we've got a general problem with compliance between different devices. I've already alluded to the most intense concentration of electronic devices in our world today. Where was it?
You talked about the cows.
The what?
Cows?
Not the cows, no. No, where do you find more electronic, thank you, Gerard. Where do you find more electronic devices than in a typical R&D lab? In the hospital, yeah, exactly. So if you're in a hospital and you're trying to make a heart monitor work with all the other monitors, right, the last thing you want is an interference detail. And then next door you've got a huge magnetic rendering system. You've got massive interference between products. So there's a whole push at the moment to, there's an ANSI standard on wireless compliance, which is about making sure that different devices don't screw each other up. And hospitals have got a huge problem on their hands. So back up in the cloud, so now the cloud is where you rent a space. You rent a space from Amazon Web Services called Rowlands' wife's contact button, okay? And it's dedicated to me, no one else can use it hopefully. And it knows that when this button is pressed, it goes back to my Wi-Fi network. That does something. So how do we determine that we have security on the connection? How do we know that some idiot isn't going to somehow, intentionally or unintentionally, pretend he's activating the button in my device? Now, if it's just a matter of sending me an email, it doesn't matter. But if it's a car going through a stop sign on the road, Park Expressway, it's a big deal. So security is a big issue. Does anybody remember what happened last year? No, of course you don't. But last year there was a major denial of service problem. Denial of service means, actually it wasn't that. It wasn't denial of service. It was, when you put a name into a web browser, the resolution of that goes through, what's it called, Sharon? The process of resolving your address from the name.
DNS.
Yes.
DNS.
DNS, thank you, yes. So there's
domain names system.
Yeah, thank you, domain name system. Here we go. So basically there was a huge DNS problem. The company that provides 90% of DNS services worldwide got hacked because what they did is they invoked all the IoT devices that are out there that aren't secure, and that was most of them last year, invoked them to fight back and destroy its DNS system. So security is a big deal. You may think this is a $5 item. You can't worry about security. You can get it. And the security systems that are being built in now use full public-private key encryption. And this stuff is all being built into the machines now. So like the new Cortex CPUs that are coming out that are going into IoT devices have encryption engines built in using public keys to get into the cloud, public keys to get back to authentication. Because the last thing they want is to have China controlling our bridges and stop sign and all that kind of stuff. So our test opportunities here in the cloud are kind of difficult because how do you pretend you're a Chinese hacker if you're not Chinese? Sorry to be tough on China, but whatever. A hacker. So how do you test the susceptibility of your things to being hacked? Challenge. I don't think Keysight has a solution. I think anybody has. Just moving on a little bit. I talked a bit about the interfaces, and you know, there's lots of different interfaces. We talked about Bluetooth. We talked about Zigbee for lights, Wi-Fi, of course. Wi-Sun is what your power meter works off, your electric power meter. Sigfox for the San Francisco sewer system. Now, the existing LTE system, does anybody know what's the typical data rate you can get of a good LTE connection on your iPhone 5, wherever it is. So if I go speed test on this to my local AT&T carrier, what speed will I get? In megabits. How many?
30.
30? The advances on 30?
So this 1 gigabit.
1 gig?
So that's
You're good.
the working.
I mean, typically it's between 5 and 1 gig. I mean, it's surprising to find a phone in a rural area here urban area here that's more than about 50 megs. So 50 megs, do we need 50 megs to send the temperature of a cow once a day? We don't do it. How much bandwidth does our existing LTE network use per channel? So when I make LTE connection here, how much bandwidth am I using? Can you guess? I'll tell you the frequency is about 700 megs, right? 700 megabits. So I send a little burst of data. How much frequency do you think I'm occupying when I send that burst of data? Faculty or whatever it is. You need to know these numbers because you're going to have a job in here in 2.5 years' time. You don't know this answer. So typical LTE is between 20 and 50 megabits. So that's a lot of bandwidth, immense amount of bandwidth that you need to occupy for a short time when you transmit your picture or whatever it is you're sending over the internet. But you don't need that much for sending a cow's temperature or changing the thermostat. So they've developed new standards for they've developed new standards for IoT that are particularly designed for IoT scaling. So they're actually very low data rate, but also very low cost ways of providing service. And this is a eye chart. You don't need to read this. There's posters, by the way, at the front door. As you go out, there's posters that Keysight put together that cover all this stuff. You can have those if you want. The whole point is scaling the cellular connectivity down to your use model, down to your cow or your thermostat. And what's going on today is that there are companies out there that are reselling service from existing carriers. So, who's it gone? One of my devices here, I just got this week and I've lost it already. There's a little modem. Here it is. This plugs into the USB. It's got a phone number. I can send a text message to this because it's connected to an existing LTE network. This is the LTE antenna. And I'm using a 20 meg bandwidth service. So when I send my text message or when I send some data out, like a position of a sensor or something here, I'm occupying a 20 meg channel only for a very short period of time. It's very wasteful spectrum, but it's a way of getting to market early. So what these companies are doing, this is a company called Hologram. What they're doing is they're reselling service from existing carriers. And then as the new standards, the new narrow standards come out for narrowband IoT and CAT-M, they will move up over to those. And as I mentioned earlier, global roaming without provision. That means you don't have to talk to Mr. Nepalese phone company when you want to look at the moisture content of your trees in the fall. The price, 40 cents a month. Pretty cool, huh? But the data price sucks. So it's 60 cents per megabyte, or you can go for a wacko plan of $3.99, gives you a whole 10 megabytes. So you get 10 megabytes for $3.99. What kind of plan are you guys on? Anyone got an idea what their plan is? 20 gig? Are you using 20? Are you using 20?
Me, myself.
Hmm?
Me, myself.
Yeah.
My family, maybe.
Yeah, okay. Yeah, so 10 meg's not going to cut it, is it? So this is not for that purpose. This is designed for low data rate, massively parallel, massive numbers of devices. 40 cents a month, 60 cents a megabyte. Pretty cool, huh? And you don't need a provision to go outside the country. So our key is making sure it all works. We have this battery drain method measuring method that I mentioned earlier. So here's the current draw of a typical IoT device. This is actually a Fitbit. The Fitbit only draws about 10 milliamps for about half a microsecond, 500 nanoseconds. Then it goes quiet again. And it's got a little heartbeat timer inside that's using the battery. It wakes it up every 30 seconds to see if it's needed. So by having very, very low duty cycle on your device, you can spread that battery over 1, 10, 15, 20 years. And measuring that is a challenge because the turn-on voltage of Fitbit is about 250 milliamps, about a quarter of an amp. So when you're actually transmitting something, you want a lot of power. But when it's asleep, you want very little power. So it's fractions of a microamp. And the test challenges of measuring dynamically signals that go from microamps to milliamps in short periods of time is very challenging. Because you're going multiple orders of magnitudes, you can't build an A to D converter that spans that whole range. So Keysight has done some very innovative work, in specifically for IoT, with what they call the source measure unit. And there's all kinds of methods of looking at different standards. Here's one where we look at the Zigbee signal. Zigbee is very simple. It has a 4-point constellation on a circle. And here what we're doing is looking at the constellation pattern and measuring the EVM. See the EVM here is 2%. So that means the fuzziness of this dot, it indicates a 1, 0 or a 0, 0. The fuzziness is measured by the radius of a circle that contains 90% of the dots. So measuring EVM is something concrete that you can do to make sure that your Zigbee connection is good. What I do wrong, you know that one. And down here you can actually decode the data. So you can actually get the ones and zeros that are being transmitted over your Zigbee directly from just an antenna snooping the signal. Bluetooth. We talked about Bluetooth. I don't really have time to do the demonstration here properly, but Bluetooth occupies 79 individual carriers, each 1 megahertz apart. So 79 megahertz of bandwidth, and each carrier occupies a 1 megahertz slot for a short period of time. And if we fired this up with a Bluetooth signal, we can do it afterwards perhaps, you'll see the Bluetooth signal marching through all those 79 slots. And we can measure the power in those slots with a spectrum analyzer like this. So that's the presentation on testing. IoT is here. IoT is a large amount of height. And as you go out into the engineering world, you're going to be possibly working in it, as long as you don't get siphoned off in software, which is very usual. We need RF engineers, we need hardware engineers who are au fait with this technology and are prepared to do the deep dive that's necessary to make these devices work for 10 or 15 or whatever years. And the challenge to you guys is to stay on top of this, grab your advantages when you can. In your senior projects, try and find something that's in the IoT space, because nothing looks better on a resume than having an IoT project when you go out for your job interviews. So let's have some questions. That's my presentation. And afterwards we can come up and you can have a look at these things a little bit more if you're interested.
At this time I would like to thank Rob for the such an interesting presentation. So let's give him a hand there. I'm sorry that I need to go and for a class. So
and if some of you have signed up for the RF lab in the spring, having heard me talk, you may want to reconsider it. I'm going to be teaching the RF lab, I believe, along with our new faculty member. So I think, are you going to be in my lab? You said you were.
Yeah, we really encourage all the students who are taking the RF course to take the lab, because it's really helpful to grasp things. It's hard to just read about these things and understand it. So we hope that everyone will consider taking the RF now. And it's also offered to the graduate students.
So when I taught the lab this spring, I said to the students, I'm preparing you for the job interview. That's the one thing I'm here for. Because you've got all the theory from Dr. Betts and others. I'm not going to write any equations on the board. I'm going to be playing with test equipment, trying to actually do real measurements, talking about railroad situations. The classic question that I gave to the class in the spring was how much power is this cell phone receiving from the tower? This is a preview. Anyone know? How much power and dBm or microvolts, whatever you want, dBm is the best answer. How much power is needed to make the cell phone operate from the tower, wherever it is? Anyone know? Well, I'll give you some choices. 0 dBm is a milliwatt. Okay? So minus 10 dBm, 10 to the milliwatt, and so it goes. Minus 100 dBm is 10 to the 10th. Right? Yeah. Anyway, the cell phone is a crappy antenna. It's only got a battery, needs to last all day, and the tower is miles away through buildings and all that kind of stuff and storage. Any guesses? Between 10 and 150 dBm and minus 150 dBm.
Minus 70, I would say.
Right. Any guess?
Minus 80.
Minus 120.
Minus 120? I don't think you're really whatever. Over here, any guesses?
Minus 100.
Most cell phones, actually Androids are better than iPhones. You can get the iPhone, but the Android, if you go into Android settings and go into About Android, you're good enough. And look up somewhere there in the menu, you can actually see what your receive power is. It's incredibly low. It's about minus 130. You go to the top of the class. Probably be
So how does that vary with as you rotate the phone?
Good question. That's a good question. So, you know, you're having an argument with your wife or girlfriend. You're not going to hold the phone straight, are you? So that's where you as engineers out there in the real world have got huge challenges. How do you make something that's less than perfect? And how do you make an IoT device, in fact, a cow, successfully transmit signals from the cow pasture into the farm? Interesting. So I like to see people think about real world numbers. I mean, minus 120 dBm might not be much to you at the moment. But if you look at 100 minus 120 dBm on the spectrum, it's almost enormous. Noise level, what's KTB? Minus 148 dBm or something. You know, we're close to theoretical limits in terms of how our cell phone network is being engineered. It's wonderful. So any questions? Not getting any questions. Come on, you must have things you're not sure about. Things I lost track of.
You also mentioned in the class you cover SDR, software defined radio.
SDR. Okay. Not going to talk about SDR?
No, but you do cover it in the lab, right?
Yeah. And thanks to Sharam and Fareed, we actually purchased these little $20 SDR radios. You can buy on Amazon for $20. This is one, it's not actually the same one, but for $20 you've got a radio receiver. Kind of cool, huh? So what we did in the lab in the spring was we actually got people to transmit music from their iPhones or Androids into a signal generator. We ran it through a whole chain of RF equipment, and through an antenna, and then back down through another chain of RF equipment. Then we decoded again. We got the music transmitted across our system and played back on the SDR radio. But those are the components you'll need when you're out working in the industry. You need those components. You need to understand it. Quiet. This is not good. Any questions? Is the pizza here? Ah, that's the problem. Should we have the pizza, then we can talk? We've got half an hour before we have to clear out of here.
Yes.
Yes.
It's a break, call that number, you know, the
Okay. I'll give you the number and you can call it. I've spread everything all over the world here, so you may not find the right little doodah. Here we go. There's the number. And where's the doodah? Where's that little LTE thing I get? Is it up there? Yeah. Send me a text message. Just don't call it. It won't call. Only text it. So at the moment, this thing's drawing 7 milliamps. And he's going to send me a text message. If everything's working, a little light will light up here saying, hey, buddy, you're okay. There we go. That's it. Let's do it again. So this is Arduino compatible. I can plug this into any Arduino device, and that can open them up or wake up the people who aren't asking. Yes.
I had a question about Zigbee, like use with some of the channel and G-controller for Wi-Fi.
So the microwave oven.
Yeah, do you have any with that, or is it something you decide?
Well, were you here when I mentioned about this ANSYS committee that's working on interoperability? Basically, there's a committee in the American National Standards Institute addressing that very issue. The thing about the 2.4 gig band is that as well as having microwave ovens, it has Wi-Fi, Zigbee, Bluetooth, and so on. And there's no licensing. It's unlicensed line information. And interoperability is a big issue. And as you noticed, your Zigbee connection you might have to a lighting system can be affected by something like someone Wi-Fi. I don't think there's a good answer to that. I think it's all about the industry self-policing itself with understandings that allow protection. And that's where authentication comes in. We talked about security a little bit. I hesitate to get into public-private key cryptography, but that's seriously what's being talked about. And is that necessary to control a light bulb? You know, there's a 50 battle, but if it's a stop sign on the Rowlands Park Expressway, I care that connection not be screwed up by someone who could be. Should we spread the pizza around and keep talking? You want to grab some pizza or is that the way we're going to do it, right? Sure. Okay, sure.